Hello, Data 100. Thank you all for coming out in the rain. Today we're going to be talking about data wrangling and exploratory data analysis. There's a lot of demo code today, so make sure to pull up the demo on your laptop so you can work along. A lot more demo than slides today. Let's dive in. Oh, and I also want to mention, a lot of people have been signing up for the morning chats with me. There's still lots of slots available if you want to sign up. Just wanted to give a heads up. Okay, so today's lecture and Thursday's lecture will be focused on the bottom right part of the data science lifecycle, exploratory data analysis. This is going to guide us this week. So far, we spent a lot of time exploring and cleaning data, lots of lectures on pandas. And then this week, today's lecture, we're going to talk about exploratory data analysis, data cleaning, data wrangling, getting data in shape that you need for analysis. And then on Thursday, we'll be doing text processing with something called regular expressions. So you have that to look forward to on Thursday with me. So what is EDA? EDA is a very exciting process. You can think of starting out EDA as when you get a new package from Amazon, let's say. You know what's in there, you know what you bought, but you don't quite know all the details about what's exactly inside the package. And there's sort of this excitement that comes out of figuring out exactly what the internals are like of the thing you're about to open. And I think going into EDA with that mindset is very helpful. One other thing I want to point you to is this result from the very first lecture that we talked about. About 70% of data scientists that were surveyed said that EDA was a major part of their day. And I'd wager that that number could be even higher. Exploratory data analysis is something that you likely will be doing across your career as a data scientist or a data analyst, or just using these tools in any capacity. Okay, so what is EDA? Why do we do EDA? Typically, EDA is used to figure out, is this the right data? Do we need to change our data set? Do we need new data? Do we need to refine our research question? It's this iterative process that we talked about in lecture 1. So you do exploratory data analysis after you get a hold of some data. You might update your research question as a result of exploratory data analysis. You might then go get some new data. This is something I've gone through many, many times working with public agencies. You get some data from them. There's something wrong with it. You go back, right? You might discover something new and sort of update your research question. So today, when we talk about EDA, we're going to talk about 4 facets of EDA. We're not going to cover the entire gamut of every single thing EDA can be, but these are 4 really important facets of EDA. So the first, structure, we're going to spend a lot of time on structure. What does a data file actually look like? What are different kinds of data files that we might see doing the process of data science? Then granularity, what's the meaning of each row? Temporality and faithfulness we'll spend the least amount of time on towards the end. How is the data situated in time? How do we know when each record was recorded in time? And then finally, faithfulness. How much do we trust our data? Is there missing data? Do we trust all the columns? But let's start with structure. So when you think of a data set, you probably think of something that looks like this. Something you might see in Google Sheets, right? Microsoft Excel. It has rows, it has columns. Okay, those rows also called records, those columns also called fields, attributes, features. You'll see there's lots of different words for describing lots of different things in data science, depending on the context you're talking about them. And so this is tabular data or rectangular data. Rectangular data, and this is a type of data that we're going to be working with extensively in Data 100 and that most data scientists also work with extensively. Now, why do we use rectangular data? Why do we put data into this form? It's easy to manipulate, easy to analyze. There's lots of tools built for handling data that look like this. A big part of the data cleaning and wrangling process, and we'll see a little bit of this today, is taking data that's maybe not rectangular, that's not in that form, but is still data, and making it look more like that form. So for example, this is related to something you'll do later in the class. You might have a bunch of documents. Let's say you have a bunch of text emails, right? You can imagine they're like printed on pages even. Okay, that's data. There's information contained in those emails, but it's not in a rectangular form. So perhaps to put that in a rectangular form, you could construct a data set where each row represents one of those emails, and each of the columns represents a different word in those emails, and each of the entries represents how many times those words show up. We've rectangularized the data. Have we retained everything there is to know about that data? Not necessarily, but we've rectangularized it. 2 kinds of rectangular data to know about, one of which we'll work with more in this class. Tables and matrices. This is a nice distinction to understand. Tables, these are things like data frames. They're also called data frames in R, which I typically use more in my own research. What is a table? What is a data frame? You have these named columns. They're labeled. Okay, and they can be of different types. You could have a column that's a string, you could have a column that's an integer, you could have a column that's a date time. Okay, they can have different types, and you manipulate them with functions that are maybe specific to the programming language you're working with. And a lot of these functions are sort of shared. Like all the knowledge that you now have about group by and merging and filtering data, that all extends to other languages. These are common things that you'll do as a data scientist. We're just learning them in the context of Python in this class. On the other hand, what is a matrix? What is a matrix? It's related. It also has this shape. But matrices are numeric data. It's all numbers. Okay, it's all of the same type. And you manipulate it with the tools of linear algebra, co-requisite for the course, right? What are the advantages of matrices? You get super fast computation, but it's less flexible. You can't have these different types in each column. But that's all we're going to say about matrices. In this lecture, we're going to be working with primarily data frames. So, a little bit of a case study. This is from the New York Times in 2021. Okay, what's going on in this plot? X-axis, we have time over 2020 and the beginning of 2021. What do these lines represent? This gray line represents the average number of flu cases per unit time in the 5 years before COVID hit, right? 5 years before 2020. And what do we see? Seems to be like a spike right around now, right? December, going into early spring, and then it kind of goes away completely in the summertime, and then it returns. But what happened during COVID? Well, this red line represents 2020 and 2021. This was current at the time of this article. We see this giant spike in March 2020, and maybe some of that was mistaken COVID, that was accidentally called flu. But then we saw something interesting in 2021. Flu seemed to have completely gone away, right? And why do we think this happened? Why do we think this happened? People are quarantining, they're not near one another. COVID is sort of like the dominant infectious disease. Okay, and so this happened with lots of different infectious diseases. Another one, tuberculosis. And this is going to be the first demo for today. We're going to be talking about tuberculosis data. So what we're looking at here are 3 statistics that were reported by the CDC about tuberculosis, an infectious disease that's pretty rare in the United States. Okay, TB, tuberculosis. And these represent incidence numbers, where incidence is measured as the number of cases per 100,000 people. And so what do we see? Out of every 100,000 people, Berkeley-ish size group of people, okay, 2019, before COVID, there's 2.7 cases. Doesn't seem like a huge number of cases in magnitude, right? Only like 3 people out of 100,000. But we see this huge drop. That's a relatively gigantic percentage drop from 2019 to 2020, and then it stayed pretty low in 2021, upticked a little bit. These numbers don't just exist in the world, right? The CDC doesn't just report this and just have these numbers sort of ready to go, right? This came from actual data. Someone needed to go through the process of actually figuring out how many tuberculosis cases were out there. They need to go figure out how many people are out there and actually go calculate these numbers so that we can see these 3 numbers and understand something ourselves without having to go through the rigmarole of pulling in all that data. And so the first demo is going to take you through the process of starting with all the raw data and getting to this point. Okay, so imagine you're an analyst at the CDC and you've been tasked with producing these values for a report. Where do you get this data from? Where is any of this tuberculosis data coming from? Well, to calculate the United States tuberculosis incidence, you probably need to know how many people have tuberculosis. That would be useful, right? We got to go figure that out somewhere. And then we have to have some data about the US population, which we can get from the census, publicly available, no problem. So the real trick here is the number of tuberculosis case counts. And what's one place that we might get this? Well, as the CDC, we might be in communication with a bunch of different state agencies. They send us all their tuberculosis case counts. We aggregate them together, and we get those numbers up top. Where did the states get them? They probably were reported to them from hospitals and different public agencies. Today, we're going to just work on the level of state-level TB case counts. So we're going to pretend we're an analyst at the CDC, getting all of these state-level tuberculosis case counts, and we're going to go from there and try to get here. Okay, and so that's the first demo for today. We'll come back to the information on the right here. It summarizes what's in the demo. So let's go ahead and take a look at the demo, which is linked on the website. Okay, zoom in a little bit here for you. Okay, and I recommend having this open on your end as well. So what we're looking at here, Lecture 5, Part 1, Exploratory Data Analysis. Let's run the first couple cells. Run the first thing, import some libraries, import some options, okay? Now, we want to calculate tuberculosis incidence, and we need raw data for doing so. And so this data that we're going to work with was pulled right from the CDC website. We click this link here, opens up right here. We can see the CDC website might be changing right now. If we scroll down, scroll, there's this nice table here that gives us TB case counts and TB incidents across the entire United States, across different geographic regions. And so presumably as an analyst, we would get something like these 3 rows reported to us. All of this information about the number of TB case counts in each state. So that's the data we're going to be working with today. Okay, so where is the data? Where is the data? So we've saved the data for you in the data folder in a file called cdctuberculosis.csv. So if I go into the data folder, okay, if I expand this a little bit, looks like there's 2 duplicate files, but they're slightly different. One is .csv, one is .tsv. We're going to work with the TSV in a little bit, but we're going to start with the CSV. Okay, how do we explore this CSV? Number of different ways. One thing, you can just double click it. And this is a very, very useful view. Okay, we can't edit anything here. There's nothing we can change, but we can view the CSV. Now just keep in mind, if a file is really, really big and you try to open it this way, it can crash Data Hub, it can crash JupyterLab. Just keep that in mind. Okay, but if we look at this thing, we have all the data from that website. Looks very, very similar to the table. Looks really, really similar to these 4 columns. Okay, but now we have it in JupyterLab with in quotes, right? What does it mean for it to be inside of JupyterLab? We see this other field up here, the delimiter. What's going on there? So let me show you another thing. This is a nice formatted view of the CSV. Let's actually go look at the underlying file. How is this data actually stored under the hood? So if we right-click CDC tuberculosis, we go to Open With. If you go to CSV Viewer, that's the view we're already looking at right now. But if we go to Editor, and I recommend not editing anything in the file. It's not good practice to ever edit a CSV this way. In general, we see the actual text where our CSV data is stored. And so we can see there's some alignment between the 2 different views. So this number of TB cases and these blank column labels up here, yeah, kind of seeing something like that. I'm seeing some of these commas up here, comma separated values, CSV. That's where that's coming from. Okay, we have the next row right here, all the different columns, and so on. And so we can see that rows are separated with new lines inside of this CSV, and we can see that the entries are separated with commas. And something we're going to run into in a little bit is like, what if there's a comma inside of an actual entry? How does a CSV deal with that? We can see it has to do something with these quoted characters. But that's 2 ways to look at a CSV in JupyterLab that can be very helpful. But again, you don't want to edit anything in this view. This is just to sort of see what's going on under the hood. Now, if we switch back to this other view and we change the delimiter, okay, it's expecting to see commas between each entry. If I were to change this to, let's say, a semicolon, notice the view gets all messed up. It's looking for semicolons to separate each of the columns. There's no semicolons for it to find, and so we get everything kind of ugly in one row, or excuse me, one column, where each row of the file is getting its own entry. Right, and so CSV is expecting this comma delimiter. Okay. All right, let's go ahead and go back to the demo and keep going here. So that's methods 1 and 2, both super useful for looking at CSVs. I look at a CSV viewer all the time when I'm working with data sets. Okay. Let's look at method 3 now. We're actually going to open up this file in Python and explore its contents programmatically. So what is this data doing here? We're going to open the file in read mode. That's what the R is. Okay, as F, we're going to iterate over that file using enumerate. So we're going to get an integer back along with the contents of each row, and we're going to print each row. And what ends up happening here, we get an output that looks pretty similar to the top of that text editor. So we look at the very top of the text editor here, number of TB cases, US jurisdiction, this totals. We get exactly the same thing. We have some extra spaces in between each of the outputs here. And the reason that's happening is because of print. Whenever you call print, it adds an extra new line at the end. And so what's going on? How can we dissect this a little bit more? So we can use this other function to see what's going on under the hood. How does Python actually know to look at the next line in the CSV? How does it actually know to do that? It uses a special character, \n. This represents a new line. The backslash is the escape character. Putting an n there gives us this special character denoting a new line. How can I actually have it print out the special characters instead of interpreting it as a new line? We can use this interesting function here, repr. stands for representation. This is going to give us the raw representation of each row. So this code is exactly the same as before, but now instead of printing out the row, we're printing out this raw representation of the row. And if we do this, we get a better sense of what the CSV looks like under the hood. Notice at the end of every line of a CSV, there's a \n indicating a new line. And then print adds its own new line, so it's printing these out one by one. Okay? And so that's one way to iterate through a CSV as well using Python. We'll use this technique to iterate through lots of different files in the class. Okay? Step 4, the most sort of common method you'll use, aside from maybe looking at the Jupyter Lab Explorer, is actually using pandas. So pandas has a nice built-in function, read CSV, aptly named. So we can read a CSV. We pass into read CSV the file path. We run it. We get a data frame. Again, looks pretty similar to what we had in the CSV viewer before, right? We had those couple blank columns towards the top. We have US jurisdiction here with the years. We're getting the same thing as a data frame using pandas. Okay, let's keep going here. So there's some problems. We can see we have these like funny unnamed columns. Instead of giving us blanks like the CSV viewer, pandas is filling in a column label for us. We're gonna have to deal with that somehow. And then this first row also looks kind of weird compared to the other rows. Notice that this first row is more of a label. US jurisdiction is really labeling what's on the left side here. What jurisdiction are we counting tuberculosis cases? Whereas the 3 columns on the right, these all represent counts of cases in each of these states. Again, you're that CDC analyst who's getting all this data. But 2019, 2020, and 2021, presumably those are not counts. Those are something else, right? Those are really labeling maybe the number of counts in each of these states in each of those years. So really those should be the column labels. And so we need to tell pandas, don't use that very first row as the column labels. Don't use this number of TB cases row in the CSV as your column labels. Use the next row down. Okay, common thing you'll have to do with a data set. So if we scroll down, we use this argument called header to indicate to pandas where are the column labels located. Header equals 0 is the default. Use the very first line in the file. In this case, we want to say, go look at the second line in the file. If we go back to the text editor view, we can see that the second line in the file has the column labels. And that first row, we don't necessarily need in our data frame. We could do something else with it later on, but for now, we want pandas to basically ignore everything above that header line and use that line as our column labels. So going back to the demo now, if we scroll down, run this, we now have a data frame that looks the way we want. Yes, so we have US jurisdiction labeling that first column, and we have each of the year labeling the counts in each year. So we've now wrangled our data into a format that we can start using, analyzing, calculating incidents with. Okay? All right, 4 methods for looking at a CSV. Let's go ahead, and I think we're going back the slides from here. So let's head back to the slides. So just to re-emphasize what we just talked about here, on these demo slides, the right side is a summary of what's going on in the demo. Okay, we're looking at tuberculosis data from the CDC. Again, each of the rows in a CSV are delimited by a new line character. At the very end of each line, there's a \n, and then each field is delimited by a comma. We learned this function pandas.readCSV, and then finally, this is just repeating what we saw earlier about tabular data. CSV is really a canonical example of a tabular or rectangular data format. Okay? Okay. Let's keep going. So we're going to come back to that first piece about structure. We're going to come back and talk about different file formats. But now I want to talk about granularity here, second step here. What does each record in the data set really represent? What does each datum represent? Data is technically a plural word. Multiple datums are data. What does each datum represent? We think of each row in a data set as maybe an individual observation. We'd hope that it's an individual observation. But what is an observation? Right? What is an observation? It might be a group of people, might be an individual person. But one thing I want to note too, this is something that you'll run into. Some people say data as a plural, some people say it as a singular. You'll hear both. Technically, grammatically, data is plural, and it's really the data show. I still say this, either's fine. Either's fine, but you're going to hear both of these out in the real world. Either's fine. Okay, so granularity. What does each row in a data set actually mean? What does each datum mean? So in some cases, each observation might represent a particular person. This is fine-grained data. If we want to have anonymous data about people in the United States, it's probably not good to release a data set that's this fine-grained, because we can start identifying people in that data set. We want to make sure people have privacy. So we might aggregate our data in a different way. So we might have a group in each row. We might have one state in each row. And then we might have really coarse data where we start mixing groups all together. And so this idea of granularity is really important to think about as you look at a data set. What does each row actually represent? Okay, so it might represent a single purchase. Let's say you're working at an e-commerce company. It might represent a single purchase and one. Back? Okay, great. It might represent a single person, or it might represent a group of users, depending on the data frame you're looking at. Data can be stored in lots of different ways. Some data is going to include what's called a roll-up record or a summary record. We actually saw this in the CDC data, and I'll point it out in a minute. These are really useful for humans. It's really nice for us to see sometimes these totals that are an aggregation of a bunch of different rows. But the problem is that you end up getting overlapping data. So when you're running analysis, these can sometimes trip you up. And then finally, you want to think, how are these data actually aggregated? If we have coarse data, how are they aggregated? So in the case of the CDC data, we're summing up over all the people in each state and counting the number of cases. Right? We might average. Right? We might do something else. And with that, let's go head to the demo. So we're going back to the demo now. Same demo as before. Let's talk a little bit about granularity. Okay, so granularity of records. So take a look at this tuberculosis data frame that we had before. So this is what I was pointing out before. Each row, we'd hope, represents a state, right? Everything below there represents a state. But we have this row up top. It's like useful when we look at this data set, like, oh, that's like nice to know that the total across presumably all these different states are these values. But when you're actually running analysis, these roll-up records can pose a problem. And I often have to remove these when I run my analyses, because otherwise you might double count, right? This row contains people who have tuberculosis in Alabama. This row also contains people who have tuberculosis in Alabama. If I forget to remove that roll-up record, that could cause problems later on. But again, roll-up records are useful as humans looking at data. Just keep that in mind. In analysis, they can pose kind of a problem. And so what is the granularity of that first row? The granularity is the entire United States, right? This is summed over all 50 states. Each row here otherwise represents a particular state, okay? So let's actually go check. So let's make sure that this data is valid. Are those actually the tuberculosis totals across each state, or they may be accounting for something else? Could they be accounting for things other than states, US territories overseas, right? Could something else be in that total? Let's go figure it out. How will we actually play with this data to figure that out? So what we're going to do to start this is we're going to drop that first row. Remember that pandas functions like this are copy on modify. When you make a modification like this, when you run .drop, it's not modifying the original object unless you use that in-place argument that we saw before, unless you overwrite it. So this is just temporarily dropping that first row. So now we're only looking at states here, only looking at different states. And let's go ahead and run .sum. So when I run this line of code here, I'm saying drop the very first row, the roll-up record, and then sum over all my different columns. So what happens? Looks kind of nasty. What is going on here? So we got a series back, okay, instead of a data frame, and we have a series representing each of the columns we saw before. When we sum everything up, right, we're adding the individual elements. What does it mean to add strings together? They get concatenated, they get strung together. So it seems like string concatenation is happening in that first row. What's going on in this row? Why are we getting 8, 7, 5, 8, 1, 8? Let's scroll up to the data and see what's going on. Why, when we're summing these numbers, we're getting really, really strange numbers? There definitely weren't that many people with tuberculosis. If we scroll up to 2019 here, we can see the count was 87, Alaska 58, 183, 87, 58, 183. For some reason, pandas thinks these numbers are all strings and not actually numbers. Why is it thinking that? Why is it thinking that? You can look at the data set for a second and think there might be something there that's telling pandas, interpret that column as a string instead of a number. Maybe just take a second, think for a moment. Is there anything there that looks a little bit funky? You might notice that there are some commas. Again, human readable. That's really nice for us. That's really nice for us to see 2000 with a comma there, especially when the number gets really long, right? But when Pandas sees that, unless you tell it to do something specific that we'll see in a minute, it sees that comma, that's not a numeric character, and it infers those columns to be strings. And so we need to account for that. We need to account for that. So one thing I want to note is, like, I'm about to show you a function for fixing this. But in real life, like, what would I do as a data scientist when I run into this problem? Do I just immediately know the function for doing exactly this, right? Realistically, I would not. I would go to Google and I would say, can you remind me what the argument is to read CSV that tells pandas to ignore commas? This is like an excellent question for Google, an excellent question for an LLM, right? You might spin up a ChatGPT window, right? You might say, how do I tell? Okay, there's another one here. Okay, thank you. Okay, all right, we're good temporarily. Okay, so you can see the LLM did a really nice job here of telling us, oh, it looks like this thousands argument in read_CSV is going to help us out. Just so you know, like, I wouldn't have remembered that. Maybe after seeing this problem once before, I know that we can run into this kind of issue, but I'm not going to waste brain space necessarily memorizing all these different arguments. This is an excellent case for an LLM or for a Google search. Okay, just want to point that out here. So let's close this LLM window here. Scroll down. And so this code is helping us dissect exactly what's going on. So this is telling us the type of each column. Each of these columns are objects. Strings in Python are stored as this object type, okay? And so this concatenation problem is going on. So if we go down here, this is what we just solved. We now have two different arguments to read_CSV to help us out. We need to change the header. And then we want to use this thousands argument. Anytime you see a comma, tell pandas that's what's denoting thousands. And so let's run this now. We run this. If we look at this data frame, does it look like things have been fixed? Is there anything that's indicating that things might be better just from looking at the data frame? We look at the very, California's gone, but if we look at the very top row, notice there's no commas. The commas are all gone. Okay, that seems like a good sign to start, but to test things out, let's actually go run sum again. We're going to drop that first row. We're going to run sum. We get counts. 8,900, 7,100, 7,900. Those look the same as the very first row of our data set. And so we're in shape. We just did data validation. We just checked if we add up all the states, do we get the actual sum that they reported? Or was there something else in there? It looks like that's just a summation across all the different states. Notice we're still getting that string concatenation issue for US jurisdiction, right? We probably wouldn't want to sum across this column in the future, but I'll leave that exercise to you if you want to fix that problem. Okay, makes sense? This iterative process, going through, finding an issue, asking an LLM, asking Google, how do you fix these particular problems in a data frame? Super common in data science. Okay, let's go back to the lecture. So, same questions we just talked about. What does each row represent? We just saw we had this roll-up record, and then we also had these state-level records. Back to structure. Back to structure. How do we deal with multiple files? Very often when you get data from some organization or from your own organization. It's not in one of these like nice little data sets like we give you a lot of the time in Data 100, right? It's stored across many different files, right? They might not all. How do we handle all those different files? We're going to have to merge data. Take two. Okay. Everyone can hear me now? Okay. All right. For folks on Zoom, hopefully you can hear now. Sorry about that. Let's go back to the lecture. Hide floating meeting controls. All right, good. That was the next slide. Okay. Another demo. Oh, yeah, it's over the thing. Yeah, thanks. Cool. Okay, let's go back to the demo. All right. So one thing I want to note, we've got lots of different things to cover today. Okay, we try to keep the demo as sort of streamlined as possible, but I wanted to keep this in here. We're not going to go through the code in this section during the lecture. I want you to run all of it. But this section is a really nice example of how you can go from raw data from a public website, like the actual raw data that when you click download on the US Census website, you get into a format that we're going to use in this demo. So I just want you to click through this code for now, but this is definitely worth reviewing because this is a process you'll go through a lot in the future. So let's go through here. I just want you to run this code, and I'll show you what the output is at the end. This is pulled directly from the census website. We end up with two data frames. Here's one of them. We've got some geographic area of the United States on the left here. So we have clearly a bunch of states. We have Puerto Rico here. We also have some regions. We have the entire United States. And we have it for all the 2020s. Remember that we need to get data from 2019 for this tuberculosis problem. And so further up, we did the exact same thing. Oop. Uh-oh. Data Hub's not behaving here. Quick refresh. Cool. Just rerun these. Okay. Okay, this is what I was trying to show you before. We also have a data frame that looks very, very similar for each of the regions in the United States. We have some funny things going on with naming here in this dot. The code in this section deals with that dot. We can see We also have population counts across all the different 2010 years. Okay, so we have 2 different census data frames that we're pulling into our analysis now to get populations for each state. So if we scroll down, I'm going to rerun these just in case they didn't run before. And we're now here. So this is the main section here. How do we actually join in the census data to the tuberculosis incidence data we just saw? So this is a nice example of merging. So let me give you a sense of what's going on here. So what I'm doing is I'm displaying our original tuberculosis data, but I'm just showing you the last 2 rows. I'm just showing you the last 2 rows just for demonstration. There's another 49 rows above this, okay, for a bunch of different other states and that roll-up record at the very top. And then we can also see the last 2 rows of our census data frames. Notice we get a little bit of overlap here. These both have Puerto Rico. This one does not. This one has Wyoming. It looks like these have Wyoming too. And so ideally, we want to have all the Wyoming data in the same row so that we can run analysis with these population counts and these tuberculosis state counts, okay? And so how do we do that? How do we actually do that? How do we merge these data frames? So we're going to use something we learned about last time. So we keep scrolling down here. One thing we can do to simplify this problem a little bit, we're only interested in getting these tuberculosis incidence outcomes for the years 2019, 2020, and 2021. So we've just deselected all of the other years, or we've actively selected 2019, 2020, and 2021. And now what we're going to do is we're going to try to merge these data frames. Okay, again, on this left column, we're going to merge based on those state names. And we're going to try to join these data frames together. Okay, so a couple different ways to merge. Both are totally legit. We can either start with our actual data frame, some data frame that we want to start with, like the TB count data, use the merge method, and then indicate the data frame we want to merge to. Or we can throw everything inside of the pd.merge function. Either is fine. Either is fine. Okay, this is a little bit more amenable to use in like a pipeline like what we're seeing here. Okay, so I'm going to run this big merge here where I start with the tuberculosis data frame. I'm telling it merge with the 2019 census data. And the key I want you to use in the merge, the key that joins these tables together, okay, from the left data frame, the one that we started with, the tuberculosis data frame, I want you to use the US jurisdiction. And then I want you to merge with all rows that have the same value in geographic area from the right data frame. And then we're doing that one more time with the 2020 and 2021 data set. And we're going to run just one of these merges in a sec to see what's going on. But see what the final result sort of looks like here. We have the data from the tuberculosis case counts here. This looks very similar. For some reason, _x is appended to each of the years. A little bit funky. Okay. Then we also have the geographic area columns from the 2 census data frames. Notice that they have exactly the same data as this US jurisdiction column. So it seems kind of inefficient to store both of those geographic area columns as well. So we'll handle that in a sec. And then _x and _y, like yes, these are variables we use in algebra, right? But they're not really useful for understanding why one is _x and why one is _y. Like what do those columns actually represent? Why are those labels given? So that's what we're going to dig into now. So to start seeing what's going on, let's just do the first merge. We're going to do just the first merge. So I'm only going to run this first part, where I merge the tuberculosis data frame with the 2019 census data. And so what happens when we do this? We're just going to look at the top of the data frame here. So take a look. Take a look. So notice that the total column that was in the tuberculosis data no longer here. There was no match for it in the census data. The only matches were for all of the states. Okay, so this row in the tuberculosis data frame, okay, got matched to this row in the 2019 census data frame. Why did it get matched? They had the same value in these key columns that we specified. They got matched on this column Alabama. And so now we can see the counts right next to one another. And hopefully now you can see a little bit more why this _x and _y is here. In pandas, it's a bad idea to have column names that are not unique, We want our columns to have unique names so that we can reference each column specifically. And so what did pandas do to try to help us out? Well, the columns in the tuberculosis data frame are labeled with a year. The columns in the census data frame were also labeled with the year. 2019 was in the right data frame. It was also in the left data frame when we were conducting this merge. And so we don't want to have non-unique column names. And so pandas is helping us out and saying, well, I'm going to go ahead and throw an _x on the first one and an _y on the one on the right. This is just the default option that pandas uses. Maybe we want to use something a little bit more descriptive, something that references maybe that these are case counts, tuberculosis case counts. How many people had tuberculosis? And this is something having to do with population. So that's what we're going to go through now. That's what we're going to see in a moment here. So again, when you're starting out and you're not having done a lot of these joins before, you understand this concept of a join, but maybe you're like, what's that name of that argument for modifying the end of each of the column names? Maybe you remember that that's called a suffix. And you're like, how do I use the suffix as argument again? Great thing for an LLM, great thing for a Google search, right? How do you use it in this case? Well, this is the same call that we had before, same exact code, but I've now added a little bit of a new line. We have a new argument here, suffixes. Suffixes. And what a suffix is saying, it's saying instead of using _x, use _cases. Instead of using _y, use _population. Okay? If we run this, we get exactly the same merge, but we get much more useful labels. And using labels like this is not only just easier to read, it's going to help make your code easier to understand. It's going to make your code more reliable. You're not accidentally going to reference the wrong column. Notice we now have 2019 _cases and 2019 _population. We've replaced the _x and the _y. We're now going to put this back into the original merge that we did. So we're now going to merge in the 2019 census data along with the 2020 and 2021 census data using the exact same syntax that we've seen here. So scrolling down, okay, this is what we just saw. Excuse me, this is what we just saw. This is what we just saw. But we're also going to add another step here. We're going to throw out this geographic area column because it's a duplicate. Notice that this geographic area column and this US jurisdiction column, because we matched on those keys, they have identical contents. And so I'm going to drop the geographic area column. It's just storing duplicate data. Okay, so I'm dropping the geographic area column, and then I'm doing exactly the same thing with the 2020 and 2021 data frame. If I run this, this looks a little bit better. US jurisdiction, just in one place. Great, we don't have extra columns indicating the jurisdiction. We have the case counts for each of the 3 years of interest. We have the population counts for each of the 3 years of interest. Okay, we're in business. We're in business. Okay, we could calculate state-level incidence at this point. How do we calculate incidence? This is a nice metric to know about. What exactly is incidence? So the census reports incidence as the number of cases per 100,000 individuals. And we saw that the census, or excuse me, the CDC, excuse me, not the census, reported 2.7 cases for every 100,000 individuals in 2019, 2.2 2020, 2.4 in 2021. This is the cases per 100,000 people. To make this a little bit simpler to start with, let's just compute the number of cases per person. In other words, if I were to randomly select a person, what's the probability that they had tuberculosis? Presumably that should be a pretty small number. Tuberculosis is pretty rare. Okay, so how do we get the per person incidence? Okay, we take the number of cases in the population, the total number of TB cases, and divide by the total population. Okay, the total population. So let's do exactly that. We're adding a new column to our merged data frame called per person incidence. And we're calculating it by taking the values in the case count column and dividing by the population count column to get the per person incidence. So let's run this, see what this looks like. Very similar data frame to what we had before, but we now have this new column, per person incidence on the far right. Very, very small, as we expect. What's the probability that a randomly selected person has tuberculosis? Probably quite low. Probably quite low. Why do we report it in terms of every 100,000 people? Numbers like this are hard for us to understand as humans. We think in like single digits, double digits, triple digits. So we need to scale this up somehow. So if we have now the per person incidence, how many tuberculosis cases are there per person, but we want the cases per 100,000 people, we multiply by 100,000. So we can do exactly the same thing to get the incidence per 100,000 individuals. We take the incidence per person, scale it up by 100,000, and that'll give us our incidence for every 100,000 people. Okay, so we now have incidence for every single one of the states here. We have the per 100,000 incidence for each of the states. One thing you might note here, this is just for readability, if you're wondering why there's an underscore here. Other languages don't have this, like R doesn't have this, and it gets very frustrating, but Python has it. If you ever want to denote where like 1,000 separator is in a number in Python, you can use an underscore. Okay, super useful. Okay, so we're just about done here. Let's now get the entire United States tuberculosis incidence. So we're going to sum over all of the different tuberculosis cases from 2019. We're going to do the same thing for the population. So we're getting the total number of tuberculosis cases in the United States, the total number of people in the United States in 2019, calculating the per person incidence exactly the same way as before. We get 2.7. What was the number that the CDC reported? 2.7. Same as before. Okay, so we've completely gone through the process of reproducing those CDC numbers. Okay, and along the way, we've learned lots of things about reading CSV files, munging data, calculating incidence, lots of other good stuff. And so that's the end of the first demo for today. We have another demo that we're going to get to in just a minute here. So let's go ahead and head back to the slides and talk a little bit about a couple other topics. This picture is actually from an R textbook, but I find it very helpful for thinking about the kinds of merges that we just used. All right. We took a break already, so let's keep going. Maybe we'll do a 1 minute stretch break. 1 minute stretch break, because I know doing all these demos can be tricky. We'll resume just in a minute. Stand up, stretch your legs. We'll come back in just a sec. Let's keep going here. Rest of the demos are pretty short. Okay, the next demo is pretty short. We have a couple more slides to go through now. So the next thing we're going to talk about is still in file structure. We're going to talk about different file formats. So we just talked about CSVs, comma-separated values. That isn't the only way to store data that's out there. Okay, so we have another demo to talk about a different kind of file, two different kinds. The first one we're going to talk about are tab-separated values, TSVs, pretty similar to CSVs. Okay, you're going to use exactly the same function to import these, except now you need to specify a new delimiter. So let's go back to Data Hub and take a peek at some TSVs. So we're going to go to a new demo now. So head to the File Explorer in Data Hub if you have it open on your side. We're going to go to the Part 2 demo. Part 2 demo. Okay, and we're going to talk about TSVs and JSON files. So again, run the couple things at the top, and let's talk a little bit about TSVs. So when you hear the word TSV, I want you to think CSV, but replace all of the comma delimiters with a tab, a long space. So let's actually see what this thing looks like. So we go into the data folder. Once again, before we were working with the CDC tuberculosis dataset .csv, that was a CSV file. We now want to work with the TSV file. Double click on it. Looks exactly the same as what we saw before. Identical. What's the point, right? What's the only difference here? So notice in this CDC tuberculosis CSV file, the delimiter was a comma. In the TSV file, it's a tab. What do we mean by that? Let's go look at the file editor. Right-click, open with, editor, same as before, and the file looks a little bit different. Okay, we have the same data, right? There's that first problematic row that we knocked out with that header argument. We have our real header, but in between each value or each entry is not a comma, but it's a long space, a tab, right? It's one long space, a full tab. If I were to change the delimiter in this TSV file and say, Jupyter Lab, go look for commas in this file, we get the same problem as before. We get the same problem as before. When you use the .tsv extension on a file, whatever program you're using to open that file is looking for tabs. And so if you tell it to go look for commas instead, you're going to get this nasty problem where each line is just the entire row of the TSV. Okay? Now, why would you use TSVs and not CSVs? That was like a big question of mine. Technically, for larger data sets, TSVs import faster. CSVs tend to be a lot more common, just from sort of historical precedent tradition. Okay, but for really big files, you'll get a nice little speed up if you use TSV. Okay, I think we have a little bit more demo to go through. Okay, couple pieces here. So again, to read a TSV, we use exactly the same function as before. We use the read underscore CSV function, but now we have to specify the delimiter. \t, just like how \n represents a new line, \t represents a tab character. Okay, if we use sep equals comma here, that would be the same as the default implementation of read underscore CSV. By default, read underscore CSV is looking for commas separating each of the entries. We can use the same techniques we saw before for reading the file programmatically with Python. Same exact code as before, or quite similar here. If we run this, okay. This is the CSV representation. Okay, the TSV representation looks very similar, but we see instead of commas, again, we get tabs here. And if we want to print out that \t instead of the actual tab, we can use that same repr function here, the representation function. Okay, it's going to, instead of interpreting those \t as full tabs, it's printing out those literal tabs, just like how it's printing out this literal new line character at the very end of each line. Okay, so that's it on TSVs. That's it on TSVs. Pretty much CSVs with tabs. You might see these out there. JSON's a little bit more interesting. That's what we're going to talk about now. So we're on to JSON. This is the last longer demo here. What is JSON? So this is another file type. It's the first file type we've dealt with today that's non-rectangular. It's non-rectangular. It doesn't already look like a table. We can sort of massage it into a table, and we're going to see that in a minute, but it's not a table to start with. Okay, and we're going to use slightly different data here. We're now working with some data on the senators from California, representatives from California. Turns out Congress actually publishes its own API, Application Programming Interface, and they like live update with all the amendments, bills, current Congress members. You can get lots of different data on this API if you ever want to do a project on Congress. And the other cool thing about JSON is that it has this property of being self-documenting. So notice in the CSV and the TSV, there wasn't a description anywhere that said what the file was. Wherever we downloaded that file is where we would get the description. But in a JSON, you can actually have the description within the file, typically called meta or metadata, data about data, that describes what's going on inside the file, which can be very nice, so that when you port the file around, people know what it means. So let's take a look. Back to the demo here. Let's talk JSON. Let's talk JSON. So I have a link here to the congress.gov API if you want to go check it out. There's lots of different things here. Maybe we can just quickly take a peek. Quickly take a peek, and you don't have to worry about knowing anything about APIs right now. Okay, ooh, a little dark. But we can see, I should change this to light mode. Anyway, you can see if we zoom in a little bit here, there's all different kinds of things about different bills, subjects, summaries, texts, all kinds of things. We're just going to use this to get some information on senators, but just know this is a great source of data for a project if you're ever looking for one. This just details how to actually get this data from the API. Don't worry about that for now. This data has already been downloaded for you, and it's in the data folder. Same as before. In the Lecture 5 data folder, there is a data set in there called California Congress members.json. Give that a click. What's going on inside here? Looks a little different than a CSV or a TSV. We seem to have this like list, this nested list. Members seems to have a bunch of different items. Let's see what's going on inside of members. Open that up. Get a bunch of different numbers here. Let's keep going. Let's open up the first one. Okay, we get a labeled list of information here. Derek Tran is a representative in Congress. Cool. Looks like Dave Min is also a representative in Congress. Awesome. These kind of look like rows of a data frame, or they could be massaged into rows of a data frame. We're going to see that in a minute. What does JSON look like deeply under the hood? So right now, this is just the JSON viewer, just like we had that nice CSV viewer. Right? We had this nice CSV viewer, but what does a JSON actually look like in actual text? Right? What does the actual JSON file look like under the hood? So same as what we saw before. Right-click, open with, editor. Let's go see what an actual JSON looks like. And you might notice some similarities between JSON and other things you've learned about Python. So take a look here. The first time you see a JSON file, I remember I felt a little bit overwhelmed, but you'll get used to it. Okay, there's lots of great information here. Lots of great info. So we start with an opening curly brace. In Python, that's like the beginning of a dictionary. Turns out JSON is very, very similar to a dictionary in Python. So we're going to use dictionaries now. The first key in that dictionary, members, we saw that before in the viewer. If we were to go inside of the element corresponding to that key, we have something starting with an opening bracket that looks like a list. And what do we end up seeing inside here? Well, we see another dictionary. And if we were to keep scrolling down, we get another dictionary. We get a list of dictionaries. In the pandas lecture, we learned how to turn a list of dictionaries into a data frame. That's why we learn it. Okay, JSON, you'll often get these nice long lists of dictionaries. So each dictionary here, inside of the big overarching dictionary, there's a dictionary inside. And as it turns out, there's actually dictionaries in that dictionary. And it looks like there's even a dictionary inside that one too. So you'll get a lot of these nested dictionaries in JSON. But there's lots of great info here. Okay, so now let's see if we can get this in a nice tabular format so we can run some analysis. So back to the code here. Let's go take a look inside of this JSON file. So we just did that. We just used like the viewer to go see it. Let's use those same techniques as before, these extensible techniques for reading a file line by line. Okay, so we're going to do the same thing we saw before. We're opening up the file located at this Congress file address, right? We're looking inside the data folder for a file called California Congress members.json. We're opening it up and we're working through it line by line, just like what we saw before. Same idea. The CSV printed out the first couple rows of the CSV, right? The TSV, when we did this, printed out the first couple rows of the TSV. Same idea for the JSON. So this is one way to iterate through files in Python, programmatically. Okay, but like I mentioned before, this looks like a dictionary. So let's take advantage of that and actually import this thing into Python as a dictionary, and then start using all these nice dictionary methods that you've spent all this time learning. Okay, so we're going to import this entire JSON file into Python. So notice what we're doing here. We're opening up this Congress file, same as before. We're using the JSON package. We're importing this, okay, right into Python. We're using this RB, that stands for read in binary format. Don't worry about that for now. Okay, and we're going to use the JSON package. We're going to use this JSON load function to load in the contents of that file. And then at the very end here, we're just checking the type of the resulting file. So we run this. What do we get? Congress_JSON is a dictionary, just like we expected. So we can start traversing this dictionary. Remember we saw when we inspected the file that that first element was called members. And inside of members was a list. So let's actually go look inside of there. Here's Congress_JSON. This is our dictionary from that file. We're going to go inside of the members element here. Okay, we're keying into members, and we're going to go grab the first element, which when we read before was Derek Tran. We run it, there's Derek Tran. We have Derek Tran's dictionary with a bunch of information about him. If you want to go see a picture of Derek Tran, there's a link for you right there. Okay. JSON's super common from APIs. APIs will often spit out data that's in this format. So you want to get comfortable working with data that looks a little bit like this. And so, we could inspect that JSON file because it wasn't very big. But like I said before, when these files start getting really, really large, okay, let's say you use the New York Times API and you pull a ton of different articles, you might get hundreds of megabytes, gigabytes, up to way more than that, depending on what you're working on. And opening something like we did before might not be the best way to go inspect it. What you're looking for might be like deeply nested in this giant file. Opening it up in some program might crash the program. So how would you know to traverse a JSON if you couldn't inspect it the way we did? And so let's actually see if we can get to this point by just sort of exploring within a Jupyter notebook. So Congress_JSON is a dictionary. Dictionaries have keys and values. What are the top level keys of Congress_JSON? We can use the .keys method, and we get a bunch of different keys. We can see that the keys to this dictionary, the only one I pointed out before was members, but as it turns out, way at the bottom, there was another one called pagination and another one called request. And so we could go index into those different keys. So for exploring this thing, let's go take a look inside of members here and see what we get. So Congress_JSON, we're going to index into the members element. What's the type? It looks like it's a list. What can we do with lists? We can look at elements of the list. Let's look at the first two elements. And what do we end up with? Those same two dictionaries we saw before. The one for Derek Tran, also Dave Min. And then if we kept going through this, we'd see lots of other Congress people. Okay, so that's a sort of gentle introduction to JSON. Let's actually turn it now into a data frame. So just so you can see, the other two elements of that JSON file look very different than members. Members was this long list of dictionaries representing each person in Congress from California, but we have two other elements, count, 54. What do we think that count is? Number of people in Congress from California. And then this other thing, we get another dictionary inside of request, giving us some other information about the file. We don't really need this in our data frame, right? We want to get a data frame of a bunch of different members of Congress and a bunch of different attributes about them. That doesn't seem super useful to us. And we're going to see in a minute how this gives us trouble. So we scroll down. How do we deal with JSON and pandas? Two nice functions. So you can directly try to read a JSON file in pandas like this. We're using the pandas library here, and we're using the read_JSON function, just like the read_CSV function we saw before. And I'm dumping in this Congress file path that we had before. It's trying to import the entire JSON at that path, and it's trying to import it as a data frame. I run this line of code. Problem. Okay, there's a problem. We get kind of a nasty error message down here. We're mixing dictionaries with non-series. There's something going on here. We really just want to create a data frame out of all the different members, okay, out of all the different members in that JSON file. But those last two elements, pagination and count, are sort of confusing pandas here. So we want to somehow tell pandas only look at that list of all of the members. So we'll try something else here. So instead, we're going to use that Congress_JSON members element. So let me just show you that quickly. Remember, this was just a big list of dictionaries for different people in Congress from California. Again, it starts with Derek Tran and then goes to Dave Min, a bunch of other folks. This looks a little bit more like a data frame, right? We have columns. Looks like these are sort of shared column names here. We have entries. And so maybe we can just cast this as a data frame now. So if we run this, and I'll fix my power outlet in a minute. I thought I was plugged in. We run this, we're in business. So we're using the pd.dataframe constructor. We're building a data frame out of a list of dictionaries that we pulled from a JSON. So we've now rectangularized a non-rectangular file. Much easier to work with, okay, than working with the raw JSON. Let me just double check that I'm plugged in here. Much better. Okay, great. All right, let's return to slides. We got 5 more minutes here. And please try to be quiet through, oh no, we got 15, excuse me, 15 more minutes. Good, we got plenty of time. All right. So, variable types. So now we have a little bit of break from demos, and we're going to talk a little bit about different types of variables, and then we have a couple Slidos coming up too. So, variable types. Each column typically denotes a particular variable, right? What's the date? What's some measurement? What's somebody's age? What year is it? And there's different kinds of variables, and you want to be able to use language to describe different variables. Okay, so 2 of the keywords here, quantitative and qualitative, or categorical. What is quantitative data? What is quantitative data? These are measurable numeric values, not just numeric values. Your Cal ID number is a number that's assigned to you. It is not a quantitative variable. These are measurable numbers. These are things like price, right? Temperature, age, quantitative variables. Qualitative variables, on the other hand, are categorical variables. These are categories. These are different categories. And then we can further describe categorical variables with 2 other descriptors here. We have ordinal qualitative variables and nominal qualitative variables. Ordinal qualitative variables are ordered categories. Things like grade level, right? We don't have 1.5 grade. We have first, second, third, fourth. These are discrete grades, right? Age group, we can sort them, right? We have Gen Z, Gen Alpha, millennials, boomers, right? We can shift these and order them in the right way. And then we also have nominal qualitative variables. So these don't have an order. Things like, what brand of phone do you have? Again, your Cal ID number. Okay? This is assigned, not measured. Cool, and then just one note here. Common thing that can cause problem in analysis. Store your qualitative data as strings. I had a project where we were storing zip codes as integers. If anyone here is from the East Coast, zip codes can start with 0. If we're storing that as an integer, that first 0 is just going to go away, right? We're just going to get the last 4 digits of the zip code, right? So when you have a qualitative variable, it's a nice safe default to store it as a string. Can you store it as a number, or can it be useful in analysis to store it in a number at some point? Yes, right? But it's a nice default to import it as a string, all right? Okay, let's do some practice categorizing here for a minute. So we'll think through each of these. Carbon dioxide level with like a carbon dioxide meter. You can tell I'm not a hard scientist, right? What kind of variable is this? Is this quantitative? Is this qualitative? Is it ordinal? Is it nominal? This is something we can measure, so it is quantitative. Good, let's keep going. Income bracket, low, medium, high. This is ordered, separate categories. This is qualitative, ordinal. Race, ethnicity, don't put that into an order, right? There can be overlap among categories, right? People can be multiracial, multi-ethnic, right? But these are sort of discrete groups, and we don't order them in any way. Qualitative, nominal. This might seem simple so far, but now let's try some trickier examples. Political party. What do we think here? So it depends. It depends, right? We've heard of this concept of like people who are like left-leaning or right-leaning, right? So in some contexts, you might have like left to right. You might have like Democrat, Independent, Republican, right? So in some contexts, it might be qualitative ordinal, but there's other dimensions to political parties, right? And in that case, maybe we're not ordering on the basis of anything. So these distinctions are not super fine, right? These distinctions get kind of murky depending on the case you're working in. So if it feels murky, it probably is. Okay, it depends on the context that you're working in. Another one, year. What's this? So year, these are like discrete numbers, right? 2010, 2011, right? We can put them in an order. Seems like qualitative ordinal, right? But if you're looking at like a plot with a ton of years on the x-axis and you're trying to see a trend, right? In that case, you could kind of interpret it as a quantitative variable? Again, sort of murky categories here. GPA. Technically, there's a finite number of combinations of classes you can take. And so there's a finite number of GPAs that are out there, right? And so you could think of them like categories, but it's almost continuous, right? We have people who are at 3.5, 3.51, 3.52, right? Depends. Quantitative, qualitative, ordinal. You might have GPA buckets. Okay? And then the last one here, date and time. This one is interesting. So there isn't another variable type called Slido. Let's do a Slido on this one. What type of variable is a date time? What type of variable is a date time? This is a combination of a date and a time. See how many people we're getting here. Okay. Seeing some disagreement. That's good. Most people seem to be thinking that this is a ordinal. Okay, there's a finite number of dates and combinations with times, and these can be ordered, so that would make sense. But we do have a solid cohort that's saying it's quantitative, solid cohort, qualitative nominal. In people who are thinking this is kind of murky, good intuition on all fronts here. So let's actually see what's going on here. So instead of answering this one directly here, let's sort of experiment and think about how we would build up to the idea of storing date time in a computer. I think this is a super interesting topic. When I learned this, this was fascinating. So temporality, how is something situated in time? So how could we efficiently store date times? So again, as humans, we sometimes think about things differently than computers, right? If I were to write a date time, probably look like that, right? Depending on where you're from, might have slightly different order, okay? Or maybe you have like a time zone on there or something. Okay, that looks like a string, right? If I want to just pull out the essential parts of that string and like not cheat here, let's take out the slashes, the colons. Like this seems like a minimal amount of information to tell you what date and time is based on that first row. So that's a string. Let's say I had a data frame with a billion rows. Let's say each of the date times was about 13 characters like this, right? About 13 billion bytes, 1 character per byte, right? And we get a 13 gigabyte column, pretty big. What if I could think of a way to store date times as integers? How could I use these as counts instead? Because one of the benefits is this, right? An integer takes about 4 bytes. A billion integers, we get like nice storage savings, but storage is pretty cheap, so this isn't like the best advantage. The nice thing we can do with integers is math and think about time between different dates. So as it turns out, this will seem a little bit arbitrary, date times are measured as the number of seconds since January 1st, 1970, coordinated universal time. Why is this date chosen? It was convenient at the time that this way of storing times was developed. And so we're measuring the number of seconds since that date. Anything before that date is going to be negative. Anything after that date is positive. So at the beginning of this lecture today, that was the POSIX time. Okay, add some commas. Same date in Wheeler Hall in 1950, negative. Okay, and so we can store date times as integers. Okay, and what's the nice benefit of integers? Well, we can start like subtracting these from one another, right? We can't subtract with the strings we saw before. It gets a little bit nasty. But I can just like subtract these two numbers. That gives me the number of seconds between two dates. I can divide by 60 to get minutes. I can divide by 60 to get hours, right? I can divide by 24 to get days, right? And so on. You can do math with this way of storing date times. So under the hood, this is typically how date times are stored. There can be some variation depending on the context you're working in. We'll see in a minute that Pandas does things by default at the level of nanoseconds instead of seconds. Okay, but this is the basic idea. Kind of neat. And so the Slido, technically you'd call this like a quantitative variable, I think. Okay, depending on the context, maybe you just had a situation where you're just working with a couple different date times and you're like comparing 3 different dates. In that case, qualitative ordinal. But integers are pretty quantitative in this case. We can measure the number of seconds, right, with like a stopwatch. All right, now we have 2 quick demos to wrap up today in the last 7 minutes. So two quick demos. We're going to show you the date time accessor of Pandas, and then at the very end, we'll talk a little bit about missing data and do another Slido. So let's scroll down. Temporality. So again, this is going to be a quick demo. We're using a little bit of a different data set here. This is the Berkeley Police Department calls for service data. These are different calls that people make to the police department because they need help in some way, right? And this gets stored in some police database. We have an ID, right? We have the offense we think happened during this call for service. We have the event date time. These all look like they were at 12 a.m., so maybe just the date is what's important here. And we have some other pieces inside of this data frame. Okay, but we're going to work with the date time columns here. So the date time columns here, event DT, when did the event take place? Okay, in database date, when was this information put inside of the database? And then it also looks like we have this time column here. So that 12 a.m. we're not going to use. It's really that 10:58 that's important. Okay, let's scroll down. So by default, all of that got read in as strings. So we need to tell pandas to convert those columns into date times. We want pandas not to interpret them as strings, but we want pandas to interpret it as a date time so we can start doing all that nice math that we saw. So I'm going to recast the event date time column using the pd.toDateTime function. Okay, it's going to interpret everything in that column. I get kind of a nasty warning here, but it seems to work. Notice that the event date time column now is formatted slightly different. Something happened under the hood that turned a string, this string, into something else, right? It got formatted a little bit different. It looks like pandas did something under the hood. What's going on in this warning? Pandas is having issue figuring out the format. Okay, pandas.toDateTime is pretty smart. It can go like infer kind of what you want, but it's a little bit inefficient to do things that way. Notice it's going to parse each element individually instead of doing like a nice vectorized operation, and so this is sort of slowing us down needlessly. I'm not going to go into details of how to construct one of these strings, these format strings here. Oh, am I freezing? What's going on here? Uh-oh. One sec here. Okay. So I'm going to uncomment this other line. And so what you can see here is I'm specifying the format that I want pandas to interpret that date time. So you can imagine M stands for month, D stands for day, Y stands for year, depending on whether it's capital or lowercase means something. And so depending on how date times are stored as strings, maybe in some data set that you get, you want to make sure to specify the format so that pandas knows how to read it really quickly. Okay, so I'll leave that to you to look into the documentation about formats. But notice that when we run it with that nice format string, we don't get that error, and things look pretty similar to what happened before. Okay, let's keep going here. Why do we want to cast things into date times? Why is that useful? Again, we can do math. Can anyone tell me what day of the week it was on April 1st, 2021? I can't, right? Pandas can. Pandas can. So this first row was April 1st, 2021. And pandas can instantly, from one of these datetime objects, tell you what day of the week it was. Okay, it was a Thursday. It was a Thursday, right? This is like a nice feature, right? We can figure out the month if we use this datetime accessor. So just like before, where if we use .str to indicate, hey, pandas, I'm about to do a string operation on each of the elements in this column, this .tt accessor is telling us I'm about to do something that has to do with date times for each element in this column. And in this case, I'm extracting the month. In this case, I'm extracting the day of the week. And then in this last case, what else is nice about integers? I can sort them really easily. I can sort them. If I want to find the earliest date time, I can sort by that column. And now I can see the earliest calls in this data frame were towards the end of 2020. Okay, all right. Last thing I want to show you here. What's the actual type of this date time column? It's kind of a funny representation here. The less than M8 refers to something called datetime 64. But the more important piece I want you to see here, NS, stands for nanoseconds. Pandas can be used for highly scientific data that's measured at a time scale that's more refined than just seconds. And so Pandas supports things up to nanoseconds here. So if I go ahead and take that column and I cast it as an integer, notice instead of getting a nice printout, I get a bunch of integers. Under the hood, date times are stored as integers. Super efficient that way. All right, I know we're running up on time, so why don't we wrap up the last piece on faithfulness next time. Thanks, everybody.